Right, so in this lesson we are going to be looking at the first lesson from the experimental determination of structure booklet. So I will pop this booklet onto the Google Classroom so that if you need to print it off, then you can do so. So experimental determination of structure is all about how we can find out what substance we have actually made in the lab. And there are a number of different techniques that we can use to do this. So, to start with a little introduction, in chemistry, not only are we able to synthesize products used to meet market demands, but there are a variety of techniques used to confirm that the correct chemical structure has actually been synthesized. And the methods that are commonly used are elemental microanalysis, which is also known as combustion analysis, mass spectrometry, infrared spectroscopy, proton HNMR spectroscopy, and ultraviolet or visible spectroscopy. And from each of those methods of analysis, we can obtain different information. So, for elemental microanalysis, the information that we obtain is the mass of each element present in your sample, which we can then use to work out the empirical formula of that substance. For mass spectrometry, we can get information about the gram formula mass of the substance, and we can get an idea or some ideas about a possible structure. With infrared spectroscopy, the information that we get is about the functional groups that are present. With proton NMR spectroscopy, the information is all about hydrogen. So that would be the environments of hydrogen, and we also get some ideas about structure as well. And then finally, with ultraviolet or visible spectroscopy, we use that to kind of quantitatively determine how much of a substance we've got. So it's basically to determine how much of the substance is present. So we will be looking at each of these in more detail. So we will look at elemental microanalysis and mass spectrometry today because they are often asked together. Then we'll do a lesson on infrared spectroscopy, a lesson on proton NMR spectroscopy, and then we'll just finish by touching on ultraviolet or visible spectroscopy. Now, in reality, no one technique can be used to confirm the structure of a compound. Instead, a combination of techniques is used. So we couldn't determine the structure of a substance by using just one of these methods. We would more often than not have to use 2, 3 of them. Right, so we're going to start by looking at elemental microanalysis. So elemental microanalysis is sometimes referred to as combustion analysis, and it's used to determine the masses of elements in a sample of an organic compound, which is then used to calculate its empirical formula. So to remind you, the empirical formula shows the simplest whole number ratio of different atoms in the compound. For example, ethane, which is C2H6, has a ratio of 1 carbon atom to 3 hydrogen atoms. So its empirical formula would be CH3. So, and having CH3 as your empirical formula, there isn't actually a molecule that could exist with a structure of CH3. So sometimes empirical formulas don't actually work as a particular compound themselves, but what we sometimes find is that the molecular formula and the empirical formula can be the same thing. It could be that your empirical formula was your molecular formula. So for example, if you were looking at methane, which is CH4, which is 1 carbon atom to 4 hydrogen atoms, its empirical formula would be CH4. So something to just kind of bear in mind. So in elemental microanalysis, a tiny sample of known weight is burned in an excess of oxygen. The quantities of each of the products of the combustion reaction are then determined by various methods, and this information is then used to calculate the empirical formula of the substance. So as a wee reminder, when we are doing a combustion analysis, oxygen will react with every individual element that's present. So if your substance contains carbon and hydrogen, then the oxygen will react with the carbon to produce carbon dioxide, and the oxygen will react with the hydrogen to produce water, hydrogen oxide. If the compound also contains oxygen, then that's something that we need to look out for, because the oxygen won't react with the oxygen in the compound to form more oxygen. If the compound contains sulfur, the sulfur would react with the oxygen to form sulfur dioxide, and so on and so forth. So if we look at a little example of how we're going to do this, it says compound X was subjected to elemental microanalysis. Complete combustion of 0.210 grams of X gave 0.478 grams of carbon dioxide and 0.196 grams of water. No other product was formed. Calculate the empirical formula of compound X. So when we are looking at this, we know from the products that are formed that carbon must be present in compound X and hydrogen must be present in compound X, because the carbon in the carbon dioxide and the hydrogen in the water must have come from compound X. It's not clear if compound X also contains oxygen. That's something that we'll be able to find out just a little bit later on as we get into the question. So when we're working out empirical formula, what we need when we're working out empirical formula is we need the mass or even the percentage of each individual element that's present. Now at the moment we know that we've got 0.47 grams of carbon dioxide and 0.196 grams of water, but we don't know the individual mass of the carbon and the individual mass of the hydrogen. So that is going to be our first step, is to calculate those individual masses. So that's what I'm going to do just now. So the mass of carbon in carbon dioxide is equal to, now to do this we are just going to do the mass of the substance that we're interested in divided by the gram formula mass. So the mass of carbon is 12 from the data booklet, and the gram formula mass of carbon dioxide is 44, and then we're going to multiply that by 100 to give us the percentage of carbon and carbon dioxide. Actually what I'll do is I'll just change that first wee bit and we'll just do this in 2 steps. So percentage of carbon and carbon dioxide. So 12 divided by 44 multiplied by the 100 gives you 27.272727. So I'll just round that to 27.27%. So we know that whatever mass of carbon dioxide we have, 27.27% of that is actually carbon. So the mass of carbon in 0.478 grams of CO2 is going to be equal to, so I'm going to take 27.27% and convert it into a decimal, so that's 0.2727, and then we're going to multiply that by the mass of carbon dioxide, so that's going to be multiplied by 0.4785 grams, which is going to give me 0.2727 multiplied by 478, which gives me 0.130. So we now know our mass of carbon, 0.13 grams. We're now going to do the same for the hydrogen. So we're going to start with, and I'll use a different colour just so these don't all blend into one. So the percentage of hydrogen in H2O is going to be equal to the mass of water in H2O, which is 2, because there's 2 hydrogens, each with a mass of 1, getting that information from the data booklet. And then the GFM of water is 18. And then we'll multiply by 100 to get our percentage. So that's going to give us 11.11111%. So I'll round that to 11.11%. What we are now going to do is work out the mass of the hydrogen in 0.196 grams of H2O. So that's going to be, now I'll turn that 11.11% into a decimal, so that's 0.1111, and we're going to multiply by that mass of water, 0.196 grams. Which gives me 0.0217, so I'll round that to 0.022. Now, what we need to do next is we need to find out, did the substance have any oxygen present? So we combusted 0.21 grams of X, and we know that we've got 0.13 grams of of carbon and 0.022 grams of hydrogen. So if we do 0.13 plus 0.22 and it gives us 0.210, then we know that there was only carbon and hydrogen present. But if they don't, then we know that oxygen must be present, and whatever the remaining mass would be your oxygen. So 0.130 plus 0.022 only gives me 0.152 grams. So what that means is that to get up to the 0.210 grams, that must be made from oxygen. So for the mass of oxygen, that's going to be equal to the mass of X, subtract the mass of carbon, subtract the mass of hydrogen. So that's 0.210, subtract 0.130, subtract 0.022, which gives us 0.058 grams. Okay, from there, we are then able to do our empirical formula. So it's going to be a wee bit of a squeeze to fit that in on this page, but we will try our very best. So we're going to have our carbon, hydrogen and oxygen, starting with the mass of each of the substances. So carbon was 0.13, hydrogen 0.022 and oxygen 0.058. Then I'm going to pop in the gram formula masses. So carbon has a gram formula mass of 12, hydrogen is 1, oxygen is 16. We're then going to work out the number of moles by doing the mass divided by the gram formula mass. So 0.13 divided by 12 gives me 0.0108. So we'll make that 0.011. For hydrogen, it's going to be 0.022 divided by 1, which is 0.022. And then for the oxygen, it's 0.058 divided by 16, which gives me 0.003625. From there, we are going to write in the ratio. Now, to work out the ratio, we divide by the smallest number of moles. So we look at our three numbers, we decide what's smallest, and we divide by that. So 0.00365 is the smallest number. So 0.011 divided by that smallest number of 0.00365 gives me 3.03, and we're looking for whole numbers here. So when your number is very close to a whole number like 3.03 is, we can just call that 3. If it is like 3.5 or 2.5, then you would write it in as a 0.5 and there would be a multiplication step involved. But for this one here, we don't need to do that. So for hydrogen, it's going to be 0.022 divided by 0.003625, which gives me 6.06, so that's close enough to 6. And then for the oxygen, it's going to be 0.003625 divided by 0.003625, which of course is 1. So the empirical formula is going to be C3H6O for that particular substance there. Now, if we have an empirical formula of C3H6O, there are a variety of different substances that could be the correct molecular formula for. So that could be propan-1-ol, it could be propan-2-ol, it could be methoxyethane, or it could be one or two other substances as well. So empirical formula only gets us so far. It's only telling us that the empirical formula is C3H6O. The substance in question actually could be any multiple of C3H6O. It could be C6H12O2 or any other multiple of that empirical formula. So that's the kind of limitation of your empirical formula. Now, we often take empirical formula and pair it with mass spectrometry. So we'll do the introduction to mass spec. So mass spectrometry is a very powerful technique for obtaining information about molecular masses and the structure of molecules. It requires only a very small amount of sample. The tiny sample is vaporized and injected into the mass spectrometer, where it is bombarded with high energy electrons. This energy is sufficient to break these molecules into smaller, positively charged ion fragments. These fragments are then deflected into separate ion paths according to their mass-to-charge ratio. Ions with a lower mass-to-charge ratio are deflected more than those with a higher mass-to-charge ratio. When interpreting mass spectrum, the peak with the highest mass-to-charge ratio provides information about the gram formula mass of the organic compound. So, what we're going to do is we're going to start fairly simple with our mass spec, and then we'll look at some other substances. So the example that we are beginning with is bromine. Now, the mass spectrum for bromine is shown in the diagram or the graph. So what we can see is that we have 5 peaks for bromine. We've got a peak here. We have a peak here at 81, a peak here at 79. We also have a peak at right on 160, this one here. We have a peak at about 162. And we have a peak at 158. Okay. Now, that might come as a wee bit of a surprise because, well, bromine's just Br2. So we wouldn't expect there to be 5 different ways that we could split bromine into smaller fragments. So let's have a look at this in a wee bit more detail. So bromine, if we were just to draw a bromine molecule, would exist like that. Now, the kind of issue with bromine, and we see this with certain elements, is that bromine actually exists with a fairly sizable proportion of isotopes. So you've got a sizable portion of bromine isotopes with a mass of 79 and also a sizable proportion of bromine which has a mass of 81, which is why we're getting a number of different peaks. Now, the highest mass to charge is kind of this section of the graph here. Now, when you have multiple peaks at that highest mass to charge, that is a very strong clue that you've got a sizable proportion of isotopes in one of the atoms in your sample. I have written that a wee bit later on, so you don't need to worry too much about writing that just now. But let's now take this a wee bit further. So, looking at our bromine, let's look at all the different variations of bromine that we could have. So we could have a bromine isotope with a mass of 79 paired to another bromine isotope with a mass of 79. We could have a bromine isotope with a mass of 79 paired with a bromine isotope with a mass of 81. Or we could maybe have two bromine isotopes with a mass of 81 paired together. Now, these would be what we would call molecular ions, or there will be molecular ion fragments. So when that sample of bromine is injected into the mass spectrometer, what happens is for some of the molecules that are there, the high energy electron basically just knocks one electron off of the molecule, which gives us a positively charged ion fragment. So the peak at 158, yep. So the peak at 158 would belong to that structure there. The peak at 160 would belong to this one here, and the peak at 162 would belong to this one here. Now, we also have two other peaks, because what can happen is when our bromine molecule is put into the mass spectrometer, the high energy electron can actually come in and break the bond between the two bromines, giving you two individual bromine atoms. So, what we could see then is if that bond in between the two bromines was broken, we could have a bromine with a mass of 79. Just going to move that over slightly. So we could have a bromine ion with a mass of 79. Now that process of breaking that bond knocks off an electron as well. So that bromine would have a positive charge. Everything in mass spec has a positive charge because the electrons that you're firing at the substance either knock off an electron or they break the bond in between two atoms, and that knocks both of those electrons away. Or we could have the bromine isotope with the mass of 81 being formed. So the peak at 79 would be from that bromine ion with a mass of 79, and the peak at 81 would be from the isotope with a mass of 81. So 5 different peaks in our bromine mass spec relating to 5 different possible ion fragments that we could get. Okay, let's look at another example. So for this one here, we've got chloroethane, and what you can see for this particular mass spec is they've actually given the number of the mass to charge ratio beside each of the peaks, which is quite handy. Now, looking at the peak with the highest mass to charge ratio, again, you can see that there is a couple of peaks in a very small area there. So that would indicate that we have a number of different isotopes present here. And when we look at the example, we've got chloroethane. Chlorine does exist as a mixture of isotopes. We can have chlorine with a mass of 35, or we could have chlorine with a mass of 37. So when we go to look at, well, what might some of these ion fragments be, first thing to do is to always draw out the full molecular structure and look at the molecular ion. So looking at the possible structure, so we've got CH3, CH2. Now, because we've got a significant proportion of chlorine isotopes, I'm actually going to label each of them. So we can have chlorine with a mass of 35, or we could have chlorine with a mass of 37. So when we put the structures into a mass spec, what will happen for some of them is the high energy electrons that we're firing at the molecule will just knock off a single electron, and we'll get what is known as the molecular ion fragment. Now, if we were to total the masses of each of the atoms, so hydrogen has a mass of 1, carbon has a mass of 12, and for this diagram on the left, the chlorine has a mass of 35, that will total to 64. So they peak at 64. This is the ion fragment that's responsible for it. The one on the right hand side, if we total them, we'll get 66. So the peak at 66, we now have a structure of the ion fragment that's responsible for it. Continuing to kind of look at some of the other ones, we've got a peak at 51, a peak at 49, a peak at 29, and a peak at 28. So what we'll do is we will see if we can come up with a couple of different structures for these. And a lot of the time it is just a wee bit of trial and error. So easiest way to do this is looking at the full structure and then just start breaking some bonds and see what you can get. So let's see if we can get any of these ones at 49 or 51. So I'm just going to draw the full structure out again, but I am going to be erasing part of it, so I would wait until I'm done before copying it into your notes. Right, so let's see if we were to erase or break that bond there by firing high energy electrons at it, we would get 2 fragments. So the fragment on the left has a carbon and 3 hydrogens, so that would be 12 plus 3, which would give you 15. Now 15 doesn't feature on that particular spectrum, but that's okay, we'll just erase that. Now what we'll do is we'll count up the mass of the remaining fragment here. So we've got 35 from the chlorine, plus 12 from the carbon, plus 1 from each of the hydrogens, which gives you 49. So again, that would be a positively charged fragment. And the peak that we see at 49 comes from that particular fragment there. Now, fragments don't have to make chemical sense. So you can see that the carbon atom here has only making 3 bonds, but that's okay because these are fragments. Okay, they're just parts of a molecule, so it doesn't matter that it's not like a proper molecule. When we look for the one at 51, it's just going to be the exact same structure, but this time we'll have the chlorine with the mass of 37. Alright, 37 Cl, and again just popping that in a square bracket with a positive sign on it because they're all positively charged ion fragments. So at 51 we'll have a fragment like that. So we've now got 2 left. We've got a 29 and a 28. So I'll just do this in a wee bit of space up at the side here. So again, just looking at that full structure. Let's do 35 and Cl. So again, it's just a wee bit of trial and error. Now, because these ion fragments only have a mass of 28 and 29, the chlorine on its own has a mass of 35 or 37, so we can definitely say there's not going to be any chlorine present there. So we'll take the chlorine out. Now let's look at what we've got left. So we've got 2 carbons and 5 hydrogens. So if I add up the mass of the 2 carbons and the 5 hydrogens, that actually gives me 29. So we can pop that fragment in a square bracket, and that fragment there is responsible for the peak at 29, and then the one at 28 will be the same structure but with 1 less hydrogen, so a couple bonds being broken here. So what we'll do, this will do something like that there. and that's responsible for the peak at 28. Okay, so the presence of more than one peak at the highest mass to charge ratio appears only when there is a sizable proportion of more than one isotope of an element in the compound. So it doesn't always appear. And in fact, much of the time when we are doing questions on this, we are looking at compounds that contain carbon, hydrogen and oxygen, and there is not a sizable proportion of hydrogen, carbon and oxygen isotopes. For the most part, most of the hydrogen on Earth is hydrogen with a mass of 1, most of the carbon is carbon with a mass of 12, and most of the oxygen is oxygen with a mass of 16. So we don't always need to consider these isotopes. It's very specific questions that deal with the impact that having isotopes can have on mass spec. So let's look at some examples. So I'm not sure why we're going straight into example 3, but what we'll do is we'll just make that example 1. It's probably just a wee typo. Right, so let's look at example 1. So we've got the simplified mass spectrum of pentane, and some of the key peaks have been labelled with their masses. So we've got 72, 57, 43 and 29, and what we're going to do is we're going to look at getting some ion fragments for these particular structures. So looking at pentane, now we've got the simplified mass spectrum of pentane given to us, so what we can do is we can get our structure from there. So we would expect the peak with the highest mass to charge ratio, and that's the peak at 72. And you can see that that peak at 72 is on its own, it's by itself. So that tells us that we're not really dealing with isotopes in this question. So when we go to look at the mass to charge ratio or the ion fragment for that peak, we would expect it to just be the full pentane structure, but with an electron having been knocked off. So if we work out the gram formula mass for pentane, we can see that it is in fact 72. So for that, I'm going to draw in all 5 of the carbons, all 12 of the hydrogens, and the only thing that's going to change here is we're going to pop this guy in a square bracket and pop a positive charge on it. And all that's happened to that particular pentane molecule is when it's been hit by those high energy electrons, another electron has knocked off it. When we go on to the mass to charge ratio with a peak of 57, we're just looking for a fragment that has a mass of 57. And bear in mind, you can break any bond. You can break a carbon to hydrogen bond, you can break a carbon to carbon bond, and you can break them in any place that you want. So for this particular ion fragment, let's have a wee look. So if we put in 1 carbon with 3 hydrogens, we will have a mass of 15. If we add another carbon with 2 hydrogens attached to it, we're going to add 12 plus 2. Then if we add another carbon with 2 hydrogens, we'll add another 12 and another 2. And then what we'll do is we'll add another carbon and another 2 hydrogens, which will give us a mass of 57. So for that fragment there, it's that bond that I've circled in yellow that has broken. Right, for the fragment at 43, it will be 3 carbons. And for this particular fragment, it would be that bond there that I've just circled in yellow that has broken. And then we've got a final one of 29. So for this one, it'll just be a little small fragment here. Like so. And that'll have your mass of 29. Alright, when we go on to our next example, which is example 2, we've got the simplified mass spectrum for pentan 3-one. Now, for me, it's probably going to be easier if we actually write the full structural formula for pentan 3-one, which I'll do in the box with the iron fragment. So our highest fragment has a mass to charge ratio of 86, so we would be expecting that to be our molecular ion, which again is just the full molecule with just one electron being lost. So let's write this in. So we've got our structure here, and we'll put the little positive charge on that there. So we're now looking for a mass to charge peak of 57. So for this one here, what we could maybe do is we could look at breaking this bond here. So if we were to break that bond there, then the fragment on the left would have a mass of 71, which is not one of the peaks that we're looking at. So let's consider breaking that bond there. So 12 plus 3 plus 12 plus 2. That's going to give you a mass to charge of 57. So it's a wee bit of trial and error. So that would be your peak there. And then we've also got a fragment at 29. So again, just look at breaking bonds, and we will see that if we are to break that bond there, we will get that fragment there. So there is a third example, and what I would like you guys to do is to have a wee go at this third example. If there is any of them that you cannot get the correct iron fragment for, please let me know. But also what I would like you to do is to have a look. So example 3 is pentan 2-one and example 2 is pentan 3-one. So these are isomers of each other. But what you can see is that there are different peaks. So they've both got a peak at 86, which you would expect. But pentan 2-one has a peak of 71 and a peak of 43, which aren't being picked up on the spectrum for pentan 3-one. So you can get some clues for the structure by looking at the mass spec, because there are some combinations that aren't actually possible based on the structure that you've actually got. So when you have a wee look and fill in this table, you will maybe see a fragment that appears in pentan 2-one that wouldn't be possible in pentan 3-one. So I will let you guys have a wee go at that. Like I said, if you're unsure, please drop me a wee message. And then there is an exercise, it's exercise 2.5. That's available for you to have a go at. It's all about elemental microanalysis and mass spec. So again, any questions, please just let me know.